These are a little bit more explanations and on each individual use cases. Again, electric drive validation. Everyone is familiar with ANSYS strategy in terms of system validation, system integration, and system validation. This is a very generic and very broad type of representation, from functional safety, software, system integration, from a component validation to the system validation. ANSYS Maxwell, as any other physics-based solver within ANSYS portfolio, stays with the component level design. And here, it's an example of ANSYS Maxwell solution for electrical machine design, where the output, input and output of Maxwell design, Maxwell can read CAD geometry, can apply the best practices on imported CAD geometry, generate the output, or reduce the size of FEA finite element solution into system validation for system integration for the entire electric powertrain. This is, the typical flow where Maxwell, can comply with a safety regulation from beginning, from importing, the proper CAD, maintaining, the best practices on setting, the design space, the design, the component design, and extracting the characteristics and the know-how from this component into the system simulation for electric powertrain. This is the electric drive at the system integration, assuming that Maxwell is importing a CAD, is starting from a geometry, assigning materials, providing a proper excitation and boundary conditions, and the proper setting of the solution. It's either quasi-static solution or a dynamic solution or a more transient solution, time-stepping solution, generating the proper reduced order model for that particular component. And here we are talking about the traction motor or any other electromechanical electrical component, to be able to integrate this high fidelity 2D or 3D physics through equivalent circuit or reduced order models for high accuracy and speed. And again, Maxwell component as part of system integration simulate together with other components coming from other potential physics as a source of energy, battery coming from computational fluid dynamic, or embedded software coming from embedded code software of ANSYS, or other power electronic components, inverter topology, bus bar coming from other products of ANSYS, or even from other simulation of Maxwell solution. Those needs to be brought together into the system and simulating together. This is a system integration. This is more on the user side, and providing the corresponding measures to identify the hazards, to identify the potential malfunctions of the software generating the characteristics and the know-how required by system integration. This is the advantage of system integration from a user standpoint. Bringing all these components, it's validating the system before any hardware is built. This is a clear benefit for any system engineer integrator. System level design trade-offs and optimization, it's much easier and more reliable to optimize the entire system at the level of circuit system simulation, rather than to have the 3D physics based coupled together for optimization strategy. As a solution provided by ANSYS, generate a complete workflow with different integrated model level coming from different physics-based solution. And as I mentioned, integrate the hardware system with the control software. Hardware system in our case relates to reducer models coming from 3D physics-based solution, and the control software, it's embedded control code into the system simulation. For the second use case, electrical machine as a virtual test, again, starting for already well-established best practices by the IEEE standard 1812, when the support of University of, and as an acknowledgement, support of University of Kentucky, the Spark Laboratory, we've been able, to generate this type of, virtual simulation, the virtual test environment, and to validate this virtual test bench against against the standards which are defining the hardware type of, testing capabilities. Definitely, I'm not going to go through every single, bullet point here, because those are based on, are compliant with the standards of IEEE 1812. 1812 standard define the lab test procedure, and mention, how these, hardware equipments are coming together to be able to measure various quantities and to derive those quantities against, standard compliance to be able to fulfill the standard requirements. Defining, how to measure, the quantities like voltage, how to consider friction and windage losses, how to measure, the total open circuit losses, and formula behind of those quantities. Again, the standards, specify how the hardware test bench is going to be developed, is going to be built as a dynamic setup, as a statistical setup, how the motor, quantities, how the motor electrical machine is going to be driven by different mechanical fixtures, and how the sensors, and the hardware, are going to be mounted into the test bench, to be able to capture, the quantities and to translate those into a digital, format. And the last, things, how these, characteristics are going to be measured against the safety regulations. As a virtual open circuit test setup in ANSYS Maxwell, we've been able, to fulfill, to go through all these, standard requirements from a laboratory, test bench, and translate those into a virtual language, into a software, setting. And those are the best practices, on how to use Maxwell, and how to use the capabilities in Maxwell, solution against those, to fulfill those, requirements. And this is very typical, virtual open circuit test, how to set up, 2D or 3D open circuit test for a given electrical machine configuration, how you simulate, the transient, how you use the transient solver to simulate the back MF to obtain the voltage waveform, to obtain the cogging torque, to obtain the core loss. All these quantities are very well, standardized by these regulations. And here, you can see, how those signals or these waveforms are considered by the standard definitions. Same type of, comment relates to the short circuit test, because the short circuit test, it's a little bit more complex, and defining the proper setup where the electrical machine is driven and is measured against this short circuit, defining, the relationships between the quantities measured in the test, and calculating all these parameters related to the short circuit, like RMS short circuit current, RMS line open circuit voltage, synchronous reactance, external impedance, and so on and so forth. Those quantities are validated and are calculated, and definitely, the results of ANSYS simulation are going to feed, those quantities, and to further validate and to compare the values obtained from simulation with the standards. And again, those standards are based on IEEE 1812, which has a very specific and strict, regulations on how to perform such such tests. Hmm. As a summary of this presentation, um, and potential application behind automotive. As I mentioned at the beginning of this presentation, the standard of ISO 26262 came as a natural, consequence of rapidly growing electronic parts within the automotive, within the road vehicles. In the similar fashion, much earlier in let's say early 1980s, the aerospace industry embraced a similar standard, and the similar standard in aerospace is called DO 178, which in nature it's similar with the ISO 26262 in terms of topology, configuration, architecture, requirements, identification, failure, failure mode identification, definition of the hazardous events, and providing the guidelines to mitigate, to minimize the risk, and so on. But it's very specific to aerospace, and is not only related to electronic components. This obviously, the 178 in aerospace evolved, and including also the electric and electronic components, and embrace the full electrified platform, especially in the last decade, where more electric components or more electrification platforms are part of aerospace developments. In automotive, the first ISO 26262 has been released in 2011, and this addressed to any type of electric and electronic component related to electrified platforms like electric drive system, powertrain, drivetrain, electrical machine design as a component part of the system, and with the final, steps into the validation and verification through hardware in the loop and signal software in the loop as well. Revision of the ISO 26262 in 2018, and extended this safety compliance with semiconductors and their application. Introduce more applications on the high-tech industry related to automotive, and here we are talking about to mention very few of them: wireless systems, EMIMC, analysis, power supply devices, and so on and so forth. You can definitely see the impact of this type of safety compliance regulation from automotive to high tech and aerospace on all the electrified type of platform as a systems, and obviously its own subsystem and components. With that being said, I thank you very much again for the time and the patience to listen to a completely new topic on software simulation environment, from a component to the system. And here how Maxwell comply with ISO 26262 safety regulation.